today. It's my pleasure to introduce our speaker, Colin Firminger. Colin obtained his bachelor's degree in mechanical engineering from the University of Calgary in 2012. Now, he then took 2 years of academia before studying a master's degree in 2014, working with our local bone specialist, Dr. Brent Edwards, here at the Human Performance Lab, to study metatarsal stress fracture risk in minimalist versus traditional footgear. After receiving his master's degree in 2016, he decided to extend his time in Dr. Edwards' lab and is now a PhD candidate investigating the mechanical fatigue behavior of human patellar tendon and to identify extrinsic interventions to decrease patellar tendon strength during running and jumping. Now, Colin has received a number of awards and accolades in his time here at HPL, but one scientific accomplishment he is proud of is a research project that he put together with his fellow graduate student, his friends, Sasha, and the then postdocs, Mike and Jared. He mentioned that he enjoyed a lot the challenging experience of putting together a research project without the input from the supervisor. But then the fun was interrupted when they need research expenses for the project. Now, Colin's industrious nature is reflected in his daily life outside of work. His recent project has been on renovating his basement, and he was very proud. And at the same time, we are very happy that he finished the electrical installation without injury. And he also took up pottery recently. And if you're going to receive a gift from him during this Christmas, you know what you're gonna get. Now, as the winter is here, Colin is excited to have finished data collection, which allows him to go on a few guilt-free ski trips this year. I hope you have fun. Now I will hand over to Colin, and he will speak on the effects of different clamping techniques on patellar tendon fatigue testing.
All right, thank you. Okay, thank you. So to begin with, this talks a lot about patellar tendon, so I'm just going to briefly introduce a little bit about the patellar tendon. Its main purpose is to transmit force from the quadriceps muscles to the tibia. You can see it here. It runs from the patella down to the tibia, and it's just this band of tissue. And because of what its function is, good. Okay. It's highly loaded during eccentric maneuvers such as jumping, cutting, and running. Now, the patellar tendon is comprised mainly of these parallel type 1 collagen fibers that run from end to end. They make up about 80% of its dry weight. So it's essentially just a big, thick band of tissue that transmits force from one area to the other. Now, one of the main factors of patellar tendon is that it has this limited metabolic activity. And this study by Kaliakowski et al. In 2005 kind of illustrates this pretty well. And what this study did was it used positron emission tomography or PET scans to look at the effects of exercise on the quadriceps muscles, patellar tendon, and the quadriceps tendon before and after. And you can see in these two images here, this is both following a bout of exercise. In the quadriceps here, it's very lit up with red, meaning that there's a lot of glucose uptake in that region. Whereas if you look at the patellar tendon in this region right here, there's not a lot of glucose uptake. In the graph here, if we look at the actual values of it before and after exercise, before exercise is shown with the white and after exercise is shown with the black bars, we can see that there is a significant increase in glucose uptake. So there is some metabolic activity happening in the tendon. But if you compare that to what's happening in the muscle, it's nowhere even close to what's going on. So it has some metabolic activity compared or induced by exercise, but not a lot that's going on. In addition, there's very little collagen turnover that occurs once the tendon is matured. So there's another cool study that was done by Heinemeier et al. In 2013 that used this unique technique of basically estimating how much carbon is in the tissue to see how much turnover is happening. So between the years of 1955 and 1963, there was a lot of nuclear bomb testing that was going on because of the Cold War. And the atmospheric amount of carbon-14 was skyrocketing, basically. And you can see that with this black line here. That's the atmospheric levels of carbon-14. And so what this study did was it actually took cadaveric samples out of Achilles tendon cores, and they quantified how much carbon-14 was remaining in those samples. So they did this in the year 2000. And basically what they were saying is if this tissue is not really turning over at all, then what we should expect to see is a similar amount of carbon-14 within the tissue that kind of potentially aligns with the birth year of this person or some sort of time after their birth. And what they actually found, if we look here at the gray squares representing the Achilles tendon samples they had, and the x-axis is the birth year, a lot of the samples that were actually sampled in 2000 had carbon-14 content in them that was reminiscent of when this period of increased nuclear testing was going on. So this kind of indicates that this tissue is not really turning over at all compared to other tissues. So if we look at the skeletal muscle that they also tested here with these white circles, we can see that they have barely any carbon-14 content in them when they were tested in 2000. And if we look at the amount of carbon-14 in the atmosphere at the year 2000, it was pretty negligible. So their argument is that skeletal muscle is turning over quite rapidly, so it doesn't have much carbon-14, whereas with this Achilles tendon they were looking at, there's very little turnover. So they hypothesized that it was about after 17 years of development, it pretty much stays constant, so you're not really getting much turnover after that. So because these tendons have very limited metabolic activity and little collagen turnover once they've matured, they're susceptible to overuse injury. And one of the most common overuse injuries in the patellar tendon is called patellar tendinopathy or jumper's knee. This is commonly diagnosed as pain at the inferior patellar pole. So if you look at this sagittal MRI here, we can see the patella and the tibia, and the patellar tendon is this black band of tissue running here. We can see this region of increased signal right there, and that's usually where people present with symptoms in the clinic. And these symptoms can get so bad that people can definitely no longer play sports, but they can sometimes no longer even go up and down stairs because it's just too painful. So like I mentioned, it's got a high incidence, or because this tendon is very highly loaded in eccentric activities, sports that involve jumping have a high incidence of patellar tendinopathy. So volleyball and basketball both have very high incidences of this, hence the name jumper's knee. Now, one of the main problems with patellar tendinopathy is not that it's life-threatening or anything, it's just that it has a poor recovery time, essentially. So once you're diagnosed with this, it's very hard for it to heal. So there's a 4-month average return to sport amongst athletes who have clinical pain. And as well, one study showed that 50% of athletes who have knee pain still have that knee pain 15 years after they've been diagnosed. And in terms of Achilles tendinopathy, which is a little bit different but kind of related to patellar tendinopathy, in the NBA, 14% of athletes who were diagnosed with Achilles tendinopathy didn't return to play. So once you're diagnosed with it, it's not necessarily a life sentence, but it's definitely a hindrance on your quality of life. And then if you're an athlete, it might make it difficult for you to return to sport. So the way that we're looking at tendinopathy is from the view of mechanical loading. And the pathophysiology of tendinopathy or jumper's knees is very debated in literature. However, a large part of the pathophysiology is mechanical loading. Without mechanical loading, we won't usually get tendinopathy. And not just any mechanical loading, not mechanical loading where we maximally load the tissue and it just ruptures. It's from this repetitive submaximal mechanical loading known as fatigue loading. So many cycles of loading at a magnitude that's lower than what the tendon would rupture at, essentially. And over time, this can cause a few things. The first one is microdamage accumulation in the form of either disorganization of the nice parallel collagen fibers, fiber kinking of those fibers, and if it gets bad enough, it can actually lead to disruptions in the collagen matrix. So the other thing that can happen from this repetitive loading is a biological response, which is cell proliferation, vascular ingrowth, increased proteoglycan production, as well as, at least initially, there's this increase in inflammatory markers. And this can either happen directly from the mechanical loading, or it can be a factor of this microdamage accumulation causing this response. So regardless of the exact pathophysiology, we're definitely concerned with this mechanical loading that's happening, this fatigue loading. So one of the ways that we can look at this is with the fatigue test. And this is some data that's been shown been collected by Ren et al. On the Achilles tendon. So essentially a test like this How it works is the tendon will be clamped in a materials testing machine, and it'll be repetitively loaded at a given strain. So for this sample, it was loaded at a strain of 0.06 until failure. And essentially, once that tendon fails, that's the number of cycles it lasted, and then you can build this relationship here with this data. So what we've been doing in our lab is actually trying to predict injury risk from this data using a viable model. So using this existing fatigue life data, we can make a relationship out of that data, usually a power law relationship. And if we quantify the amount of scatter present in that data, we can input it into this probabilistic analysis to actually estimate the probability that, given this data set, a given tendon at a given load and a number of cycles is actually going to fail. So this equation here, we don't really need to talk too much about it, but essentially the PF is the probability that a given tendon will fail at a certain strain and number of cycles. And the strains that are inputted into here are both nominal strains from this relationship here. So how is this data exactly collected? There's a few different ways. But the problem with trying to collect mechanical data on tendon is that clamping in the actual tendon is very difficult. There's been a few different approaches to try and clamp onto the tendon. One of them is freeze clamping. And the study that we just discussed by Ren et al., they actually used a freeze clamp on the top of the Achilles tendon here and a PMMA fixture, so like a cement fixture in the bottom, to clamp onto the calcaneus. And the point of the freeze clamp is essentially to try and make the tendon into a rigid object when it's in the clamp so that it can actually be adhered to essentially within the clamp and clamped onto. There's another example of a freeze clamp here. You can see that that clamp is entirely frozen at both ends here, and so that tendon can be clamped onto. So this works pretty well. However, some of the problems are that if the tendons or the clamps are set to be too cold, they can actually start to freeze the tendon between the clamps, and that can affect the results of the test. So it's kind of finicky, but it seems to work for some tests. The other solution that's been come up with for trying to mechanically test tendon is just through regular clamps, so compression. So you can see here there's these serrations within either end of the clamp, and then essentially there's just screws that are holding those two sides of the clamps together, and that tendon is just squished between them, and that's how it's held. So there's definitely some problems with slipping of the tendon out of these clamps, even though it looks like it's pretty well clamped in there. And the other problem that we can see is that, in this upper clamp here, that tendon's starting to kind of come out the sides. And if we look closely at a different but similar clamp, we can see that as the tendon enters the clamp here, it's still got its normal form. But once it enters the clamp, it actually starts to kind of spread out as it's squished. So these nice parallel collagen fibers that may be going along the tendon are starting to potentially change direction, as well as these serrations are probably affecting how that tendon's actually functionally going to be loaded when it's within the clamp. So this might actually change the behavior of the tendon as it's being loaded in the mechanical testing setup. So the ideal solution, yeah.
Very brief question: does it usually break at the clamp, whichever system you use, or does it ever break in the middle when you do such a test?
So it's usually kind of vague. They usually say it failed in the mid-substance from these tests, but they won't say exactly where it failed. But we'll get into that in a little bit. Yeah. So for us, the ideal solution, because the patellar tendon has two bony endpoints, the patella and the tibia, would be to clamp to the bones. And that's actually been done by this study here by Lavanito and al. So essentially what they do is they cut down the tibia so that it can be put into this clamp, and then they'll cut down the patella as well, and they'll put it into a different clamp. So they're not actually touching the tendon, they're just clamping onto the bones. This has also been done by several studies before this other one, except these studies were looking more so at using the patellar tendon as a replacement for ACL, basically. So they were just trying to figure out the mechanical properties, if those were similar at all to what the ACLs were. But essentially they did the same thing. They cut down the bones on either end, and then they clamped onto the bones and not onto the tendon. So if we were to mechanically test patellar tendon, this is the ideal situation that we'd want to use. However, this is not what we were offered when we tried to do some opportunistic patellar tendon testing. Essentially what was happening in our lab was EFOS was doing some tests on some human cadaveric samples, and he was getting whole knees. And he was just taking the femurs and the tibias. So we were basically left with the patella, but we had to cut it away from the tibia. So there was no bony endpoint there. And we also chose to cut it away from the patella as well, because we were trying to section the tendon up into different regions. So essentially, all we could do to test these opportunistic samples is clamp onto the tendon at both ends. So essentially what we tried to do was we had our clamp here, we put a piece of sandpaper and then we glued it to the clamp, and then we actually put glue on the inside of that sandpaper and glued the tendon into that. So it was not only against sandpaper for some extra grip, but it was also glued in place. And then on the outside of the clamp, which was serrated, the exact same situation. There was a piece of sandpaper that was adhered to it, and then on the inside, the rough edge of that sandpaper, we put some cyanoacrylate glue to glue the tendon in place. So we were pretty sure that it wouldn't be slipping, but we weren't sure what was exactly happening in terms of the mechanical behavior or the strain going on at the clamp. During the tests that we were running, we kept the tendon hydrated as per normal, and this is the exact setup that we had here. So we had our upper clamp, our lower clamp. You can see the tendon in between them, and then we were just running a drip over that tendon to make sure it's hydrated the entire time. So we received 10 of these opportunistic samples. We sectioned them into 60 samples. That was for a study that I'm not going to discuss, but we were trying to figure out if there was a difference between the fatigue life of different areas of the tendon. And then we essentially just loaded it between a minimum value of 2 megapascals and a maximum value ranging between 8 and 25 megapascals until that tendon failed. So pretty much the same test as what we just saw with the Achilles tendon, except we're doing it with sections of patellar tendon. And this is what we saw. So a similar kind of relationship to what I previously showed for the Achilles tendon, where we have this power law relationship that's going on between the nominal strain applied to that tendon, so the grip-to-grip strain, and the number of cycles until failure. However, there's quite a bit of scatter in this data, and that could be for a few reasons, due to the sample preparation, or it could also be due to something like the clamping setup that we had. The other thing that we noticed with these samples is that the tendons were generally failing near the clamps, not in them, but kind of close to them. And we were thinking that this could potentially be due to some strain concentrations that were occurring near or at the clamps themselves. And we were thinking to ourselves, if we could just quantify these strain concentrations, potentially we could adjust the actual fatigue relationship that I just showed for the actual strain that's happening on the tendon and not just the nominal strain that's happening in between the clamps. So one of the ways that we could approach this is with digital image correlation, or DIC. And this has been used to provide localized strain information for engineering materials, and as well as some biological materials in mechanical tests. So DIC, in terms of tendon strain mapping, is pretty straightforward. All you have to do is essentially orient the tendon normal or 90 degrees to the camera, and just spray paint a random speckle pattern onto the tendon so that it can be picked up by the camera. And then as you load that tendon, this high-speed camera records the speckle pattern as the material is loaded. So it records how that speckle pattern deforms, and then it just generates a strain map from a user-defined region of interest. So this is a study that did this with Achilles tendon, so it's clamped between 2 clamps here, and you can see that the actual Achilles tendon itself has been dyed dark blue, and they've spray painted the tendon with just white speckle spray paint, so for high contrast. And then as that tendon is loaded, you can see that they generate this strain map over the surface of that tendon. So there's definitely some heterogeneity here of the strains that are occurring on that surface. The other thing you can do is actually view the strains throughout the different images and actually calculate them over a video, essentially, as this tendon is loaded. So this is an Achilles tendon that's loaded to failure. The red areas are regions of higher strain. And you can see kind of near where it fails here, right before it fails, there's this kind of region of red that pops up, and then the tendon fails. So again, this is a different type of speckle pattern. I think they just sprayed black spray paint onto the white tendon instead of doing the inverse like the other study did, but essentially the same result is coming out. You get this nice strain map as the tendon is being loaded. And just quickly how DIC actually works is essentially what it's doing is it's taking that entire region of interest that you've defined and it's splitting it into sub-images or facets. And then as you go from the previous frame to the next frame, or the unloaded or the undeformed to the deformed frame, it's just doing a cross correlation between this reference and deformed frame. So it's calculating from our undeformed frame the position in X and Y to our newly deformed frame that's got the highest cross correlation value. And then once it's figured out where that's moved, it's going to track how that facet has actually deformed. So it'll actually track the position of the points within that facet to figure out how it's deformed. So this one's gone from like a square shape to more of a tetrahedral shape, essentially. And from that, we can differentiate those displacements and calculate strains. So it just kind of does this for each of the facets that you split, or that it splits the image up into, and it gives you that strain map out of it. So in order to test the effect that clamping may or may not have had on our opportunistic tendons that we were clamping directly onto, we decided to test 12 porcine or pig patellar tendons up to a strain of 9 megapascals. So we had two clamping situations. The one on the left we called the bone-bone clamping situation, and the one on the right we called the tendon-tendon clamping situation. So it's pretty self-explanatory. In the bone-bone clamping, we did something similar to what was done to that patellar tendon in the previous study I talked about, where we actually just clamped directly onto the tibial tuberosity. So this was the tibia that has been cut away, but in the clamp there is just the bone, and then the tendon is upside down, so in this bottom clamp here is the patella. So you can see that the tendon itself is actually freely between the clamps. In the tendon-tendon clamping setup, we just clamp directly onto the tendon like we did with the human patellar tendons. You can see the tendon within those clamps there, and that red light is just the light of the DIC system as it's recording. So this is just a better schematic of kind of what's going on. In the upper clamp for the bone-bone, we still glued it in place just to make sure it wasn't going to slip out. And we had this nice wedge clamp that we designed for the lower clamp. And this lower clamp is actually, you could rotate it so that we can change the hypothetical knee angle by rotating the patella to certain angles. But we just, for this study, left it at one angle for the entire test, or for all samples as well. And then for the tendon-tendon clamp, it was the exact same as the human tendon testing. We had the tendon upside down, and we glued it into the upper clamp, and then we glued it into the lower clamp and just pulled it to 9 MPa from there. So the first thing I want to talk about is not any of the DIC data that we got out, is actually the nominal strain data, so the grip-to-grip strain. And we can see in this graph the stress on the y-axis and the nominal strain, or the grip-to-grip strain, on the x-axis for the two different clamping setups. So the dark blue is the bone-to-bone, and the red is the tendon-to-tendon. So right away we can see that there's a lot more strain happening on the tendon-to-tendon clamping setup for a given stress level, for every stress level essentially. And when you quantify that, it's about twice as much strain in the tendon-to-tendon compared to the bone-to-bone. So it's almost like these two setups are behaving as different materials. It's much less stiff when it's in the tendon-to-tendon compared to the bone-to-bone setup. So that's kind of our first clue that something's definitely going on with the clamping here. In terms of the actual DIC results, I'm just going to explain kind of the way we chose to analyze this data. So for the bone-to-bone condition, we just defined a region of interest right between the upper and the lower clamp that went along the entire width of the patellar tendon. And that was our bone-to-bone condition. Our tendon-to-tendon condition, exactly the same thing, except the clamps are obviously closer together because we had to glue some of the tendon into the clamp itself. So the region of interest is defined between the upper and lower clamps, and that's what that one was. We also did a third condition where we actually matched the region of interest from the bone-to-bone to the size of the tendon-to-tendon. So we removed the upper part and the lower part of that strain map so that it was the exact same length and area, or physical area of the tendon-to-tendon condition to directly compare what the strains were in the bone-to-bone versus the tendon-to-tendon. So qualitatively speaking here, if we just look at these strain maps for this representative patellar tendon, we can see in the bone-to-bone condition, there's definitely some strain concentrations that are happening near the clamps, but they're about 8% strain. Whereas if we look at the tendon-to-tendon condition, there's strain concentrations as well, and they're much higher. They're greater than 12% strain, essentially, and they're extending fairly far down into the tendon itself. So it looks like, qualitatively speaking, there's definitely an effect of clamping directly onto the tendon compared to clamping onto the bone. If we try and quantify these differences, we can try and break down that distribution of strains. So I chose to use average strain and peak strain. Amongst the three conditions, bone-bone, the bone-bone matched to the region of interest, and then the tendon-tendon. In terms of average strain, we saw a significantly higher average strain in the tendon-tendon condition compared to both the bone-bone and the region-mapped bone-bone. And the same thing went for peak strain. So significantly higher peak strains in the tendon-tendon condition compared to both the bone-bone and the region-mapped bone-bone. The other thing that I looked at was the percentage of the total area that was at the peak strain of that condition. So for the bone-bone clamp, there would be this area here and this area here at peak strain. And for the tendon, it would be these kind of areas near the clamp and in the middle, and then near the bottom clamp as well. So for this percent area at peak strain measurement, we found that there was no difference between percent area at peak strain between the bone-bone condition and the tendon-tendon condition. But when we looked at the region-mapped bone-bone compared to the tendon-tendon, there was a significantly higher percentage of that area at peak strain. And that kind of makes sense. Like the tendon in the middle here there's no effect of the clamping at all, and it's able to be loaded in a more physiological way. So those strains are much lower than what we would see here because of that clamping artifact, essentially. So because our tendons were failing near these clamps, and because those peak strains were highest near the clamps in that tendon-tendon condition, we figured that peak strain is probably at least a dominant factor in how these tendons are failing, and not just nominal strain. So does using peak strain, does that make sense from a kind of mechanical point of view for a method of failure? After a little bit of looking at the literature, it seems like it is a reasonable theory, as this one study by Sheckman and Botter, who tested extensor digitorum longus human tendons, they did two tests, one with a quasi-static tensile test, so they just straight up pulled the tendon until it failed, and then in a fatigue test, they did similar to what I was doing, so they pulled it at a given load until it failed. Regardless of whether they were just doing the maximum tensile test or a fatigue test, they found that the tendons failed around 15% nominal strain. So this kind of indicates that these fibers that are reaching some certain strain level, in their case 15% nominal strain, may begin to fail, and that if a certain percentage of those fibers fail, then the entire structure just may fail as well. So this kind of pathway of failure is kind of what we think is going on. So there's this gradual recruitment of fibers as you fatigue load this tendon, and those recruited fibers will continue to creep as they continue to be under load. There'll be an increasing percentage of fibers that are creeping as more and more fibers get recruited as this tendon begins to stretch. And once a certain number of fibers reach a limiting strain, then that tendon will experience overall failure. The other thing that's kind of interest to us is the relationship between nominal strain, so the strain that's measured between the two grips, versus the strain that's measured from DIC. So for just the tendon-to-tendon clamp region, for example, when we're looking at the nominal strain on the x-axis here versus the peak strain on the y-axis, we can see that for almost all the porcine samples, we were seeing higher peak strains compared to nominal strain. So if you were just measuring nominal strain, we're not actually adequately capturing the maximum strain that's on that sample, essentially. So if there's a way to correct for this, essentially that would increase the fatigue strength of our patellar tendon. So initially, this is the fatigue relationship that we obtained from the human samples when we were just measuring nominal strain. And if we were somehow able to correct for this peak strain that's occurring within the sample, it would act to shift that relationship rightward. So for a given strain, so if we have a strain of 0.08, and the original nominal strain measure would fail, around 5,000 cycles. But if we were to correct it, it would fail almost an order of magnitude higher, essentially. So it's not actually making the tendon stronger, it's just a more accurate representation of what's occurring on the tendon as it's in this clamping setup and being under load. So this is kind of just a pilot project in order to understand what's exactly happening with different clamping setups. The real testing is actually going to happen pretty soon here, so we're actually going to fatigue test 30 whole human patellar tendons that we just got. And these tendons are not being taken from anyone else's study, they're from my study only, so we're actually going to keep the patella and the tibia attached, and we're going to clamp to those two instead of just trying to clamp to the tendon. But we're also going to do DIC during these fatigue tests. We want to measure the full field strains at different time points along the fatigue life of these tendons, so that we can, first of all, try and correlate the nominal and the peak strains with the fatigue life of these tendons and maybe get a more accurate measure of what's happening. And also try and investigate how the strain magnitude and the locations of peak strain change as this tendon starts to fatigue more and more and gets closer to failure. So I'm hypothesizing that if we can actually use DIC and get these peak strains, it might actually reduce a lot of that scatter that's present from just using that nominal strain value in the fatigue life measurements, and maybe give us a more accurate representation of what's happening to these tendons as they're being loaded in fatigue. So the take-home messages from this work are, first of all, that clamping technique definitely affects the strain distribution of the patellar tendon. If we clamp directly onto the tendon, we get these large increases in strain right at the ends, where the clamps are. Also that by using DIC, we found that these DIC measured peak strains are higher than what we can measure with the nominal strain. So that's kind of interesting in terms of the behavior of the tendon, what we think it's happening versus what might actually be happening. And then, like I just mentioned, accounting for this increased strain may actually decrease the scatter observed in the fatigue data and increase the observed fatigue strength of that tendon. So with that, I'd just like to thank my lab group as well as my supervisory committee and my funding sources. Thank you.
So I was wondering about the limitations of clamping rigidly, and it might be worth considering to drill a hole through the bone and give it a degree of rotational freedom, because you might have it oriented slightly askew, leading to more strains on one side than the other. Have you considered anything like that?
Yeah, so normally when I'm mounting it into the clamps for the bone-bone condition at least, I'll let it kind of hang so it's not being like falsely put one side under more strain than the other. But yeah, it's definitely a possibility to do that. I just would worry about the potential of it becoming a little less secure throughout the extent of a fatigue test, but it's definitely like when we were mounting the tendon samples, if you didn't mount them perfectly straight, one side of that tendon is definitely getting loaded higher than the other, and you can actually see it in the DIC measurement. So it's very tricky to get it perfectly straight for at least the tendon, but it's definitely easier for the bone for sure.
And is that because of the higher mass? Or?
It's just because you get one chance to glue it into the grips, and once it's glued in, it's not going anywhere. So it's kind of, yeah, it's just tricky. Yeah.
So when you're doing these fatigue testing, do you know if there's, like, could you predict where that, like, the fracture is going to occur? Mm-hmm. Or is there any literature out there on where those fractures are going to occur?
So I mean, if we're looking at the clinical or the literature describing the location of tendinopathy in the patellar tendon, we would expect it to be kind of near that patellar pole where failure would essentially occur. But I think if we can use this DIC, we'll be able to hopefully see regions where the strain is the highest. It should hopefully be where that tendon is going to fail if this mechanism makes sense at all. So like once if the region under the highest strain, the fibers fail there, then that's where the whole tendon should start to fail as well. So hopefully that's what we see. But yeah.
Can you go to that slide, DIC?
This guy?
No, the other one that is maybe more red.
This?
Yeah.
Yeah?
Why is it red in the mixed substance there?
Yeah. That's a good question, and even in the article itself, they don't really have a good explanation for what's going on. I mean, to me, what I'm thinking is that there's just we think of tendon as this homogeneous structure of these parallel fibers that run the entire length, but I mean, this is showing that there's definitely some heterogeneity there in the material properties. So there's regions of potentially increased stiffness and less stiffness.
The material properties or the way of loading? You know, you could be a little bit asymmetric in loading.
Yeah, that's true too.
And something like that too.
That's true, but we would expect, I would think then we would see like an entire increased strain on one side of the tendon or something like that. But for just to be like increased right in the middle, I'm not sure. It could be doing to the loading as well, I guess, for sure. But I think it might be tendons are maybe a little bit more heterogeneous than we originally think they were. So.
I mean, tendon, in my understanding, ruptures typically because of asymmetrical loading.
Mm-hmm.
You apply always a symmetrical loading. How does that? You know, if you would do the same test, then you would have, instead of a symmetrical loading, an asymmetrical loading with high stress on one side.
Right.
probably get a different result, correct?
Well, I would assume so. Yeah, I would assume it'd be
And
weaker.
that the result would, in my view, correspond more to what's happening in the reality, in real life.
I mean, there's definitely some asymmetry in how the tendon's strained as it's under load, but I feel like it's mostly it's not in the frontal plane, I don't think, as much. I think a lot of that might come from what you said. Maybe it's potentially due to how it's been clamped. But if you look at the anterior side versus the posterior side of the patellar tendon, this is the Achilles, but for the patellar tendon, there's definitely differences for a given force applied to the entire tendon, it'll strain different on the anterior versus posterior.
And your cycle number will change too.
Potentially, like if you have a big strain concentration at one part of the tendon because it's either because you haven't clamped it properly or if there's just this asymmetrical
Have you
loading.
ever tried to do that?
No, not intentionally. There's definitely been some.
Why not?
I was trying to just create a uniform loading on the tendon. I feel like that's the best case scenario because if I start to change things like the angle, how they're clamped in the clamps, and that's another source of variability that's going into these fatigue life measurements that may or may not be actually happening in vivo. So I feel like that would just introduce a lot of variability that would be in addition to what I would be trying to measure, essentially. So I'm just trying to keep it as consistent as I can for at least for the last study, when I was clamping directly onto the tendon.
But without consistency, by doing it asymmetrical.
I guess if you put it in at an angle or something like that, then you could introduce some asymmetry there, yeah. But at least for what I was trying to get out of it, for just a normal relationship between strain on the entire tendon and the fatigue life, we just wanted to keep it straight.
Do you think tendon ruptures in real life when a symmetrical load is applied?
I mean, I'm not exactly sure what you mean by symmetrical load. Essentially, there's a force that's applied.
Load over the whole tension.
Pardon?
Load over the whole tension. Same load over the whole tension. Over the whole tendon.
I mean, so the quadriceps muscles are pulling on the patella, right? And then the patella is pulling the patellar tendon, essentially. So there might be some force asymmetry there between the different quadriceps muscles that might be pulling the patellar tendon one way or the other. But I'm not sure if I could quantify that into a fatigue test, first of all. And second of all, I'm not sure if that would generate a big enough change in strains from the medial to the lateral side to illustrate failure in one half or the other. I'm not sure.
Well, Benno's question sparked another question in me. So you're looking here at rupture, but your question originally was about tendinopathy,
Yeah.
which is arguably occurring way before rupture.
Right.
So in that
Right.
sense, rupture has not that much bearing on that. But so how are these related? Is it like if a tendon would rupture sooner, it's also gonna develop tendinopathy sooner, or are there other factors that are?
So we would essentially something like that. So we would expect that if we're loading a tendon at a higher strain, this more microdamage would accumulate. The likelihood of developing tendinopathy would be greater, essentially, for that. Or for, if you're loading it lower but at a higher number of cycles, it really depends where it lies on that nonlinear relationship. But essentially you're right, we're not trying to predict failure, we're trying to predict tendinopathy, but we're using failure relationship to do that, and that's why it's probabilistic and not like your tendon will fail here, you will get tendinopathy at this exact cycle, right? It's more of a gray area.
And I have another question. It seems to me that in reality, or so you mentioned that jumper's knee is prevalent in baseball players, basketball players, and stuff like that, but maybe less prevalent in people who run, or even people who ride bikes, like the people in the Tour de France. They arguably train the longest time per day of any sport, but they have no problems. So could it be that also in some way the waveform of the force that is applied is important? Because to me,
I guess the time scale could potentially be. I think it's from frame of view, I think a lot of it is the magnitude that's being applied. So as you land from like a jump or something, the magnitude is very high as you're, trying to accelerate your center of mass upwards, essentially. And that magnitude plays such a big role in this fatigue relationship that's probably what's going to cause this micro damage. Whereas if you're bicycling, the magnitude is probably not quite as high.
Okay.
But it could have something to do with like the time scale that the load is applied over, potentially, maybe. I don't know.
Yeah.
Question?
Well, the question is, it is not from me, but from EFAS. You said, did I see correctly that the Achilles tendons from that study you showed actually snap at the lower strain region? And did the authors talk about why that is?
I assume he's talking about this video. This is just on Twitter, this video, so there wasn't really much explanation to go along with it except that it's a cool video of a tendon ripping with DIC. So I'm not really sure what they were analyzing or anything like that for refos, but it does seem to rupture somewhat near, I don't know if I can pause it, there's that strain concentration that kind of starts to happen here and it ruptures nearby that, but I'm not really sure. And I don't even know if this is axial strain they're measuring. I think it might be transverse strain, so like this direction of strain. So I don't have an answer for him. But, yeah.
Maybe I missed, but you said that in the tendon situation, the clamps are a bit slippery. They slip down, and if it is the case, so why the strength were higher?
Right. So for our actual testing, that they weren't slipping. We had them glued like very well in the clamps. There was no slippage because of the glue. But in other studies, they've noted that, especially for Achilles tendon, because when you clamp it at the top in this region, there's a lot of tendon to clamp onto, and if you don't use things like glue, then there is potential for slipping, and other studies have noted that the actual nominal strains are higher than the DIC measured strains because of that. So you're having this slippage, so that the clamp to clamp distance is increasing a lot more than the actual tendon is being stretched. So you get this false increase in the nominal strain compared to the DIC. But for ours, because they were so well glued in those clamps, we actually saw the opposite for peak strains. Yeah.
Yeah, and do you think that with the glue you can actually simulate the attachment stiffness of a bone tendon?
I mean, potentially the stiffness, but definitely not the physiology of it. As the enthesis, it's super complicated. I think John Sevick, one of the students who used to be here, did some imaging of it, and it's like these fibers are changing direction really rapidly as they enter the bone, and there's a lot of material property changes as they go from bony to kind of more collagen. So there's definitely no way to estimate that with our setup, but the rigidity, potentially. Yeah.
So I have a direct follow-up to Arash's question and then another one. So in the one sample that you found that the maximum strain was less than the nominal strain, I want to understand how that can be possible without slippage.
Maybe that could have been the case for that one, yeah. Okay. But on average, or for most of them, I guess it was the other way around, yeah. Okay,
and then my other question is, so tendons will have a superficial side and a deep side. Which side were you imaging, and do you think you might find different results if you look at the other side?
Yes, so we were imaging the superficial side, the anterior side of the tendon. For the next study with the whole human tendons clamped bone to bone, we're going to try and image both sides because if you look at where the tendinopathy is happening, most people say it's happening on the posterior side. And some studies have shown that this side's actually in compression as the tendon's loaded at certain knee angles. If it's happening within the tendon itself, we're not going to see anything, right? Because we can only do the surface measurement. But if it's happening on the surface of that posterior side, then we might be able to see something going on there. So yeah, we're going to try and do both sides when we fatigue test them. Yeah.
I have a question.
Yeah.
I'm not sure if I'm understanding correct. How does that bone clamp work? Because I thought tendon connect to bone to muscle.
Yeah, most tendons do, except for this one. It's a weird one. It's actually, in England they call it the patellar ligament, not the patellar tendon, and Dave Hart always harps on me for that. But yeah, it's just unique. I don't know. It's the patellar tendon, and I'm not sure why it's been called that, but essentially you have the tibia and the patella, right? So that's how we're clamping onto it. Every other tendon in the body is going to go from a bony insertion to a muscular insertion. Yeah, which is where this clamping becomes a real problem. But
Since you bring out this photo, and your setup is you have two phases clamping on the tendon on both sides, right?
for the tendon clamping, yeah.
And if you look at here, the tendon attached to the bone on one side. If you change your scenario, if you glue on one side of the tendon and do that stretch, will the glue be strong enough to hold the tendon?
No, there's no way.
That's my question.
And then you'd have the strain distribution. You know, the front fascicles would be probably being strained less than the rear ones, which are actually rigidly attached. So I don't even know if that would be any better than just clamping it or not. Yeah.
I assume this is only part of your thesis, correct?
Yeah.
What is the whole thesis about?
It's kind of a dog's breakfast. It's a lot of stuff. So the first study was the one that I did with Olivia, where we did the NBA study on different shoe stiffness and surface stiffness on trying to lower Achilles and patellar tendon strains during jumping. So that was motion capture. And then the next study that I'm going to try and put into my thesis was the stuff that we did with Sasha and Mike.
Oh, the unsupervised one.
But thanks for the money. Thank you. And then this would be I'm not sure if this is going to go in or not, the clamping stuff, but then the last part would definitely be the human tendon stuff.
So what is the over?
Just trying to understand how the patellar tendon behaves in fatigue scenarios, essentially, and the cumulative load that's occurring on that tendon as we fatigue load it, essentially.
Did you select that topic?
I came back to do a PhD because the NBA project sounded cool. And then I realized it was a PhD and I had to do more work. So then it was a lot of discussion between Brent and I trying to figure out where to go next from that. But we were originally trying to do a study for getting participants into a biodex and trying to fatigue their tendons and see if we could actually quantify this. So if we look at the fatigue relationship, we can see that regardless of what it is, for a given load or strain, that plays way more of a role in the number of cycles as tendon, or I guess in this case, the tendon can last than the number of cycles of failure. So in this relationship, the strain is weighted to some exponent, so it's way more of a factor. So what we were trying to do is actually tease that out and see if that was going to exist in human participants by loading them at different loading magnitudes and different numbers of cycles in like eccentric loading in the biodex. But after doing a little bit of research more into that, we figured that might not illustrate any results that we wanted. So we kind of shifted and went back to a more engineering-based study, the mechanical testing stuff.
Do you know what the strain is that you're displaying from the DIC?
So you can choose if you want axial, transverse, or shear. So I was just doing axial strain for this, yeah. No. So it's a commercial software, so it's really hard to like hack into the back end and get the data out of it. It gives you the strain map. You can put virtual extensometers on the strain map if you want to get displacements, but it's not going to give you a map. It's just going to give in the discrete point that you put this extensometer. It's going to do that. Yeah.
I can give you some software that will give you that.
Okay.
More importantly, though, what I'm getting at is there's different failure criteria for anisotropic materials versus isotropic materials.
Okay.
And I think if you have the displacement map and you have that 3D strain tensor, then calculating the ideal criterion for an anisotropic material might change this plot, but then you might do a better correlation.
Okay.
Something to try.
Right.
You might have to do more work, experimental work.
Yeah. Oh, fair enough. Yeah, cool.
And about the patellar tendon, the patellar ligament, and what I always assume is the reason when you're born, you don't have a patella, right? And so you have essentially a tendon running from your tibia to your quadricep muscles, and it ossifies later. So you come out of the womb,
you have a tendon. Now you have a ligament.
Like a tendon, and then it becomes like a ligament. The composition is still like a tendon.
Right. Okay. Well, that's good to know.
I don't know if that's true, but that's
So I'm thinking about cumulative fatigue and injury and microdamage over life.
Yes.
So do you think that if you could identify where these speckled, I'm not saying the speckled mouse, but if you could figure out where the microdamage is, would you be able to then maybe predict where the tendon would fail?
That's what we're hoping to do with the next study, right? If we can, we're going to get the strain map, and we're going to be able to see where the tendon fails, hopefully. So we can kind of correlate those two, at least qualitatively.
Is the tissue human? It's probably fairly old.
Yeah, it's...
There'll be years and years of microdamage in these tendons.
Yes, that's true.
Could you not maybe take a pristine pig tendon?
Mm-hmm.
You know, some pig that's not trotted around. And could you not then, let's say, like a deep penetrating laser, go in there and invoke microdamage where you know where it is, and then when you speckle analyze it, then you see if the failure correlates to where you burned out collagen fibrils or where you coagulated them.
Yeah.
I'm just wondering if there's a way to link sites of damage to ultimate failure.
Yeah, I mean, I guess that's definitely a possibility. Or I don't know if it's a possibility or not, but it's a good idea. But mechanically, it would make sense that the region that is the most damaged would, or has the least fibers connecting it, just from an engineering point of view, I would feel like that would be the region that would fail, because the fibers that are not damaged in that same region surrounding it would have to take more load, essentially, or that much load, but for less number of fibers. So the strains would increase in each individual fiber.
So do you think that could explain some of the scattering
Yeah.
that you get from your samples, that some are in better shape than others, and they're more brittle or more friable?
Yeah, I mean, a lot of the scatter, I think, was, like I mentioned, due to like sectioning the tendons into these subsections, essentially. And also due to the clamping, potentially not having them perfectly lined up. But yeah, definitely, it could be another
Gone
factor.
back to these histologically and actually fix them, and then section them to look for
Microdamage?
microdamage?
No, never done that. But yeah, that'd be a cool idea to check out, yeah.
You kind of mentioned that, like, the tendinopathy typically occurs on the posterior side of the patella, and that it might be due to the angle of the patella causing compression.
Yeah.
Has that been shown? And then how did you choose your angle to clamp them in?
Right. For this one, so first part of the question, there's been one study that's shown with finite element modeling that as you increase the flexion in the knee, and so basically rotate the patella, this region of increased strain develops there, but I think they were showing it was tension, not compression. Another study that was actually testing cadaveric samples, they put like extensometers onto the different regions of the tendon on the posterior and anterior side, and they found that it was going into compression. But that study, I don't know, the methods seemed kind of iffy, I think, so I don't know if they're super believable or not, but there's definitely some speculation that that's compression there.
And then I guess in youth, so people who develop Osgood-Schlatters, like why do people develop Osgood-Schlatters in the tibia, but they develop tendinopathy at the inferior pole of the patella?
I don't know enough about Osgood-Schlatters to know why that would occur there.
Like, is it?
Maybe it's just like another insertional, something to do with growth, I'm assuming.
Yeah,
it's usually people who grow fast,
patella
right?
Does not have the same osteo, like the same capacity to build bone as the tibia does. So then the tibia, they could experience the same, or do people who have Osgood-Schlatters and develop tendinopathy?
I don't know if there's a correlation between Osgood-Schlatters and tendinopathy later.
Yeah.
I'm not sure.
And then I guess the part about the angle was.
Oh, sorry, yeah.
Is is there epidemiological data? Like there's variations in the angle of people's patella, right? Like some people, like there's many different things. You can have patella alta, patella baja, which physically changes the location of the patella relative to the femoral groove. But then you can also have variations in the slope of the patella. So do people who have a higher slope, which would presumably cause more compression naturally, develop tendinopathy more than other people?
Yeah, I haven't seen any research that's kind of used that as a intrinsic risk factor. I've never seen that discussed, but yeah, that would make sense.
Easier to measure than like if you wanted to predict someone who's likely to develop tendinopathy.
Yeah, no, that's interesting. Yeah, I don't think anyone's really looked at that, but that's cool.
Do patellar tendons exhibit an endurance limit or no? Because your graph here doesn't really would not exhibit that. Or you don't account for it here.
Right. I'm not really sure. I would assume there's some level, I mean, there's been hypotheses that say once you get above the certain strain, then damage starts to occur, but as long as you stay below this strain, then there should be no accrual of damage. And that's about, I think in this paper, it was like 6 to 8%. So that could be considered a potential endurance limit, but I think there's always going to be some extent of maybe potential microdamage forming and then the slow repair of that and stuff. So I don't know if there's a true, if you walk for your whole life and never do anything like that, you're going to be guaranteed to be good, but your odds are probably better.
Sorry, can I play off that? Can you go to the, because I don't really trust these data, can you go to the sort of the Ren study?
Yeah.
So at 6% strain, this thing is failing around 100,000. Well, one of them fails after 10 cycles, but in general, the SN curve is suggested 10,000 cycles.
Yeah.
So who is saying that 6 to 8% represents a good endurance limit for human tendon?
I forget the exact authors, but I know that's what they were saying. But yeah, that doesn't really make sense when you look at the actual data. But again, this is nominal strain data too, so potentially the actual strains.
Strain has to be higher than the nominal strain.
Yeah, well, it doesn't, yeah, it depends, I guess, on the clamping setup, but yeah, I would expect it to be higher.
Like,
so maybe it would actually be lasting, maybe at 4% strain, it's not actually a 4% strain.
I think in general, regardless of the clamping setup, the peak strain has to be higher than the nominal strain.
If it's not slipping, yeah, I agree, yeah.
So, but those data would suggest, if I imagine taking that curve out, that potentially there could be an endurance. I mean, that's a logarithmic fit, right?
Yeah.
So it would never stop. But in general, it looks like you could say for sure 4%.
Yeah.
If you wanted to say 1 million cycles, which your run out or something like that.
I got a question from Robert Griffith. He said, does the cycles to failure graph change depending on the frequency of the cycles?
I mean, I test them at the same frequency, but other studies have shown that if you change it by like 20-fold or something like that, it stays the same, so it shouldn't really matter. No.
And he said, perhaps higher frequencies squeeze out water, which had no time to resolve. Certainly squeezing out water makes elastin stiffer. I do not know about collagen.
And the tendon definitely gets stiffer if it dries out, that's for sure. But the tendons are kept hydrated throughout the entire test, so I don't think that would be a big issue. But yeah, it doesn't seem like the frequency of loading, unless you're like drastically changing it by like orders of magnitude, I don't think it would have an effect.
So, based on your data discovered about your graph, you loaded for so many cycles, did you control for the temperature change during that loading?
It was, I mean, I'm assuming the temperature stayed constant during the loading. It was just kept in a room. So Yeah, but no, did not control for it. Yeah.
I have one last question. Nobody else want to ask another question? So you talk about your presentation. You talk about cutting the patellar tendon into different sections.
Yeah.
To see if they have fatigue, right? Where's it done?
I was hoping someone wasn't going to ask for that, but here's the results. Okay, so quickly we segmented them. If this is just a standard axial MRI. So this is the patellar tendon here. If we zoom in on that, we separated them into anterior medial, anterior central, and anterior lateral, and then the same thing on the posterior side, so 6 sections. And then I just analyzed quickly the anterior versus posterior. So this is the data that we got with the dark blue being the posterior and the red being the anterior. So it looks as if they have almost the exact same slope, but the y-intercept's different for the two. It looks like the anterior side is actually stronger than the posterior side. It's not significantly different, but there seems to be some sort of a trend there. Again, there's a lot of different factors going on, and it was definitely tough to cut along the midline of the tendon. So I'm not sure, like Brent said, how much we can actually trust this data, but it's potentially interesting that there is this difference that we saw there. Yeah. Yeah.
Right, more question for Colin. Now let's thinking again.
So next week we have Songwon Han sitting behind, and she will tell us more about residual force enhancement of cardiac myofibrils. See you next week.